Welcome to HFCL Time Machine. Past, present, future, all connected.
Let's step into today's chapter, where we explore the hidden multi-million-dollar traffic jams happening beneath your feet right now.
Oh, yeah. It is a massive issue.
Right. Today, we are looking at a really fascinating, highly technical case study from HFCL. It is about a major U.S. service provider facing just a brutal infrastructure bottleneck.
A total nightmare scenario for them, honestly.
And the mission of our deep dive today is to explore exactly how this provider managed to double their long-haul internet capacity inside these legacy 1-inch underground microducts. And the crazy part, they did it without digging a single new trench.
Which is frankly something a lot of people thought was physically impossible.
I mean, think about it. You rely on AI, 5G, and cloud computing every single day. We all do.
Yeah, constantly.
But the physical layer, the actual microscopic glass threads buried under your streets, is what makes all that digital traffic possible.
Right. The cloud is actually just a bunch of cables in the ground.
Right. So this deep dive is about how engineering is somehow keeping up with our absolutely insatiable data demands without turning our cities into permanent, never-ending construction zones.
Because nobody wants that.
No. To really set the scale of the challenge here, I want you to imagine trying to thread 3,000 delicate strands of silk through a really long, heavily congested drinking straw.
Oh, that is a great way to picture it.
And you know that if even one of those silk strands snags or breaks along the way, the data just stops flowing entirely.
Yeah, and the financial and logistical realities for this service provider were just incredibly stark. I mean, they had miles and miles of these 1-inch underground microducts.
And a microduct is basically just a plastic pipe, right?
Yeah, exactly. They are specialized plastic pipes designed specifically to hold fiber optic cables. And those ducts hit full capacity in just 4 years.
Wow. Just 4 years?
Just 4 years. So they desperately needed to double their fiber count to accommodate this huge surge in network traffic.
Yeah.
But trenching new lines is astronomically expensive.
Oh, I can only imagine. You're talking about tearing up roads, right?
Oh, yeah. It's a massive civil engineering project.
Yes.
You are tearing up miles of urban concrete, redirecting traffic for weeks, and, navigating this total labyrinth of regulatory permits.
So the provider issues a mandate. They basically say, double the capacity, but make it fit inside the pipes we already have.
Right. Good luck, engineers.
Yeah, seriously. But normally when you want to put a cable in a pipe, you just pull it through, right? Like tie a string to it and yank.
Well, for short distances, maybe. But here we are talking about runs that stretch for miles.
I imagine the friction of just pulling a heavy cable would snap the glass fibers instantly.
Exactly. Pulling is entirely out of the question for long-haul distances. It would just destroy the cable. Instead, technicians use a process called cable jetting.
Cable jetting. Okay, how does that work?
So they use a specialized machine that mechanically pushes the cable into the duct while simultaneously injecting high-volume, high-pressure compressed air into that same pipe.
Okay, so pushing and blowing at the same time.
Right. And the high-velocity airflow travels faster than the cables is moving. This creates a drag force on the cable jacket that literally pulls it forward.
Oh, that's wild.
Yeah, the cable is basically designed to ride on this cushion of air. It's essentially floating through the underground microducts.
So the cable is surfing on an air current through the underground pipes.
Okay, let's unpack this. Because if a pipe is already near capacity, like we said, these things are full, how is there any physical room left for air to carry a new, denser cable at all?
That is the exact problem they ran into.
Right? Isn't this quite literally like trying to cram a heavy winter sleeping bag back into one of those tiny little nylon sacks, but you're only allowed to use a hairdryer to push it in?
That analogy captures the physical friction perfectly. I love that. You have a heavy object, a confined space, and a propulsion method. The compressed air, right? That is completely dependent on having sufficient volume to flow.
Volume that doesn't exist anymore. Exactly. The physics of microducts installation dictates a hard threshold. When a duct reaches an 80% fill ratio, the volumetric airflow drops precipitously.
So at 80%, the air just stops working.
Basically, yeah. There simply isn't enough empty space left in the pipe for the air to achieve the velocity needed to generate that forward drag force on the cable.
Right, the hairdryer can't push the sleeping bag.
Exactly. When you rob the air of its volume, the cable stops floating, it drops against the duct wall, the friction spikes dramatically, and the installation just stalls.
And historically, these high-count fiber cables, the ones carrying thousands of strands, they require really heavy, thick protective layers, right?
Oh, absolutely. They have to survive the physical stress of being buried. High density usually equals high weight, and high weight demands more air pressure to float.
But you can't just turn up the air pressure infinitely.
No, you can only increase the air pressure so much before you literally blow out the duct seals or damage the equipment on the surface.
So you can't change the laws of fluid dynamics. And you obviously can't magically make a legacy 1-inch underground pipe any wider without digging. So if the pipe and the air are constants, I mean, the only variable left to manipulate is the physical structure of the cable itself.
That was the only way forward. HFCL had to completely re-engineer the cable to bypass these aerodynamic limitations from the inside out.
Okay, I want to get into the material science of how they achieve that density. But first, we actually need to address a crucial point of technical accuracy regarding the terminology used in this case study.
Oh yes, I am really glad we are pausing for this.
Yeah, because if you are reading industry marketing materials or even occasionally skimming official documentation, you might see the technology referred to as intelligently bonded ribbon.
Right, you see that a lot.
But to be technically accurate, and we always strive for absolute technical accuracy here, the technology is actually intermittently bonded ribbon cable.
Yes, intermittently bonded ribbon, not intelligently. The distinction is absolutely vital.
Why is it so important to get that right?
Because the word intermittently describes the actual physical structure of the engineering breakthrough. We are not talking about a ribbon that possesses some sort of digital intelligence, or smart sensors.
All right, it doesn't have an AI chip in it.
Exactly. We are talking about the physical, mechanical pattern of how the individual glass fibers are glued together. They're bonded at intermittent intervals, which we will explore when we get to the splicing mechanics later.
So keeping things strictly technically accurate, we are talking about intermittently bonded ribbon, IBR.
Correct.
Okay, with that cleared up, how did HFCL actually shrink 3,456 individual fibers to fit this heavy sleeping bag into the tiny nylon sack?
Well, they applied a multi-layered material science strategy, and they started at the microscopic core.
The glass itself.
Exactly. The first major alteration was shrinking the physical glass. The industry standard has long been 250 micron fiber.
Okay.
HFCL transitioned to a 200-micron fiber technology.
200 microns? Just to visualize that, how thick is a human hair?
A human hair is roughly 70 to 100 microns thick. So we are moving from something about 2.5 hairs thick down to just 2 hairs thick.
Wait, if you make glass thinner, doesn't it become inherently more fragile?
You would think so, right?
Yeah. I mean, if I want a glass rod to survive being blasted through a pipe, I'd want it to be thicker, not thinner. How does shrinking the glass help anything other than just saving a microscopic amount of space?
It definitely seems counterintuitive. But thinner glass actually improves what engineers call macro bend performance.
Macro bend performance. Okay, explain that.
Well, think about when you bend a thick cylindrical object. The material on the outer curve stretches, and the material on the inner curve compresses.
Right, the outside pulls apart and the inside scooshes together.
Exactly. And that physical stress differential can cause tiny fractures. Or, in the case of fiber optics, it distorts the reflective boundary inside the glass.
Which means the light leaks out.
Exactly. Allowing light to leak out degrades the signal. By reducing the outer coating of the fiber to 200 microns, you decrease the distance between the inner and outer edge of the bend.
Oh, so there is literally less material to stretch or compress?
Yes. This severely reduces the physical stress during sharp turns. The light continues to bounce perfectly down the core.
Wow.
Meaning the thinner fiber can actually navigate tighter corners in the underground ducts without losing signal integrity.
That is wild.
And when you multiply that 50-micron reduction across 3,456 individual fibers, you dramatically reduce the overall diameter of the entire cable.
Okay, here's where it gets really interesting. Because shrinking the glass buys us some space, sure. But 3,456 fibers is still a massive bundle.
Oh, definitely. It's a lot of glass.
Even with thinner glass, traditional cables group those fibers inside thick, rigid plastic buffer tubes, right?
Yeah, standard practice for decades.
So if you still have all that heavy plastic wrapping around the groups, the cable is still going to be too heavy to float on the air current.
Right. Those traditional buffer tubes add a massive amount of dead weight and stiffness. So HFCL's solution was to completely eliminate them.
Just get rid of them entirely.
Entirely. They moved to a tubeless architecture. Instead of extruding heavy plastic pipes around the fiber groups, they utilized highly specialized, lightweight binder yarns to secure the fiber ribbons.
Binder yarns.
Yeah, they basically stripped away every non-essential gram of material from the internal structure.
Yeah.
And that drastically reduced both the mass and the rigidity of the cable.
That tubeless design reminds me of switching from a heavy, rigid, traditional winter parka to one of those ultra-thin, high-tech thermal base layers.
Oh, that's a really good comparison.
Yeah, you're trying to achieve the exact same structural integrity and environmental protection, but it takes up just a fraction of the space.
Right.
And more importantly, for the air jetting process, getting rid of the parka sheds all that unnecessary weight. It finally gives the cable a chance to lift off and float.
Exactly. The weight reduction was key.
But let me challenge this for a second. If you take away the heavy plastic armor, aren't you just blasting essentially naked, yarn-wrapped glass through a pipe?
Basically, yes.
How does it survive the intense pressure of the blowing equipment? Because you mentioned the machine literally pushing it.
It's true. Extreme miniaturization does generally invite vulnerability. During a high-speed jetting installation, the cable is subjected to massive radial compression from the tractor machine pushing it.
Right, it's being squeezed.
And it also faces intense tensile stress as it whips around subterranean corners.
So how doesn't it just shatter?
HFCL had to aggressively re-engineer the internal strength members of the cable to compensate for the missing buffer tubes. Through rigorous comparative materials testing, they optimized the reinforcement materials so that this ultra-thin, tubeless cable can withstand compressive forces of up to 100 newtons per centimeter.
100 newtons per centimeter, that sounds like a lot.
It is a massive amount of force. That internal strength matrix absorbs the crushing force of the installation equipment, completely preventing any structural deformation of the glass inside.
That is incredible.
Yeah, the signal attenuation remains perfectly stable even under the extreme stress of a high-pressure deployment.
Okay, so we've shrunk the glass so it bends better. We've ditched the heavy plastic tubes for lightweight binder yarn. And we've beefed up the internal strength to handle all that pressure.
Check, check, and check.
The cable is officially lighter and smaller, but we still have the friction problem.
Right, the 80% full pipe.
Exactly. Even a lightweight cable is going to scrape against the sides of a pipe that is 80% full. Lightness doesn't somehow magically negate physical scraping.
No, it does not.
If it touches the wall, it creates friction, and friction kills the installation.
Overcoming that inevitable surface area contact required a completely different approach to the exterior jacket of the cable.
Okay.
And this is where HFCL introduced the most visually distinct element of their engineering solution. They call it the loofah-shaped outer sheath.
Wait, like a bath sponge? Is the outside of this high-tech fiber optic cable actually soft and porous like a loofah sponge you'd use in the shower?
Okay, we definitely need to clarify that to maintain technical accuracy.
Please do.
It is absolutely not a sponge.
Okay, good to know.
Yeah, it is not soft, and it certainly does not absorb anything. I mean, if an underground cable absorbed water, it would be catastrophic for the entire network.
Yeah, that would be bad. So why call it a loofah?
When engineers refer to the loofah-shaped sheath, they're talking strictly about the precise, engineered surface geometry of the outer high-density plastic layer.
Ah, I gotcha. So it's about the physical texture of the hard plastic, not the material properties of a sponge.
Exactly. A traditional fiber optic cable jacket is perfectly smooth and perfectly round.
Right.
If you force a smooth, round cable into a smooth, round pipe, you maximize the surface area contact between the two materials.
And more contact means more friction.
Exactly. So the loofah sheath is a specialized textured geometry. It features these microscopic ridges and valleys running along the entire outside of the tough plastic jacket.
Oh, I see. By making the surface bumpy, less of the cable's physical mass is actually touching the inside wall of the pipe at any given moment.
Precisely.
It's kind of like the treads on a tire reducing the contact patch on the road.
That is exactly what it's like. It significantly minimizes the physical contact points with the microduct wall, which drastically lowers the coefficient of friction.
That is so smart.
But the texture actually serves a second, equally critical aerodynamic function.
Oh, really? What's that?
Those microscopic valleys between the ridges create channels for the compressed air.
No way.
Yeah. The high-pressure air catches those ridges, almost like the dimples on a golf ball, altering the boundary layer of air. This maximizes the air drag efficiency.
So it uses the air better.
Right. The airflow grips the texture and propels the cable forward much more effectively than it could on a perfectly smooth surface.
Wow.
It completely bypasses the traditional aerodynamic limitations of those high fill ratio installations. It is a perfect demonstration that altering the surface geometry of a cable is often a far superior engineering solution than just obsessively trying to make the cable smaller.
That is brilliant. The texture acts like a sail for the compressed air while simultaneously reducing friction against the pipe walls.
Exactly.
Okay, so we've successfully blown this highly engineered, luffa-textured cable miles down a congested underground pipe.
The hard part is over.
You'd think. But eventually, it reaches its destination, and some technician in a manhole has to actually connect those 3,456 individual microscopic glass threads to the live network.
Ah, yes. Which brings us to the splicing bottleneck.
Because splicing is where the installation timeline usually just grinds to a halt.
Oh, it is notoriously slow. Traditional high-count loose tube cables are just incredibly difficult to prepare in the field.
What makes it so hard?
Well, technicians have to carefully cut away the heavy tubes. Then they have to meticulously clean off all these protective water-blocking gels. And then they have to individually manage thousands of loose, chaotic fibers.
That sounds awful.
It is a process that takes hours of painstaking manual labor. And this is where the true brilliance of the intermittently bonded ribbon, the IBR technology, comes into play and completely solves the bottleneck.
Right, the intermittently bonded ribbon. Emphasizing the physical structure of the bond here. How does intermittent bonding actually work mechanically?
So in a traditional ribbon cable, 12 fibers are laid flat side by side, and they are glued together continuously down their entire length, basically like a rigid ruler.
Okay.
That rigidity is terrible for jetting through pipes because it can't bend in multiple directions.
Right, a ruler doesn't bend well.
Exactly. With intermittently bonded ribbon, the fibers are still grouped, but the adhesive is applied only in tiny alternating spots. It creates almost like a spiderweb matrix.
Oh, I see.
Because they are only bonded intermittently, the fibers remain highly flexible. When they're pushed through a pipe, they can fold in on themselves, they can roll into a tight cylinder, and slide past each other to navigate tight bends without breaking.
So they stay loose and chaotic enough to survive the physical journey through the pipe?
Yes.
But how does that help the technician on the other end who has to splice them? Didn't we just say loose fibers are a nightmare?
Well, here's the magic. When the technician at the destination strips back the loofah sheath, they don't have to deal with thousands of loose, separate strands.
Why not?
Because of those intermittent bonds. The technician can grab a group of fibers, pull them taut, and they instantly align and act just like a traditional flat, rigid ribbon.
Wow, they just snap into place.
Yes. This structural alignment allows the technicians to use what is called a mass fusion splicer.
A mass fusion splicer, what does that do?
Instead of melting the glass ends of one fiber at a time, the machine uses microscopic cameras and an electric arc to perfectly align and weld 12 fibers simultaneously in a matter of seconds.
That is incredible.
HFCL's design provides the extreme flexibility of loose fibers for the installation, combined with the rigid, predictable geometry of ribbon fibers for instantaneous mass fusion splicing.
That is the ultimate have your cake and eat it too engineering solution. It folds up when you need to push it, flattens out when you need to connect it.
Exactly.
But, theory and design are one thing. We can sit here and marvel at macro bending and surface geometry all day in the studio.
True.
I want to know what happened when they actually took this out into the mud and dirt of the real world. Does a 3,000 plus fiber intermittently bonded cable actually survive a real world jetting installation?
Oh, the verified success metrics from the case study leave no room for doubt. They really put it to the test.
Tell me about it.
They took the 3,456 fiber IBR cable and put it through rigorous testing at the Duraline facility in Clinton, Tennessee.
Okay, Duraline, they are a major player.
Very much so. The testing environment utilized a standard 1-inch SDR11 duct.
SDR11, what does that mean?
SDR11 is a standard dimension ratio. It basically means the wall thickness is specifically calibrated to withstand underground pressure, which tightly constricts the internal diameter.
So it's tight.
Very tight. The duct was sitting right at that critical 80% fill threshold we talked about earlier.
The danger zone.
Yes. And despite all the physical limitations we discussed, They achieved a massive jetting distance of 1.4 kilometers.
1.4 kilometers, that is roughly 4,700 feet of continuous, uninterrupted installation.
Exactly.
Through a pipe that was already almost entirely full without the cable stalling out or snapping.
It is a landmark achievement for optical density and installation physics. And they didn't stop there.
What else did they do?
They followed that up with extensive field trials using a slightly smaller 1,728 fiber version of the IBR cable in 25 over 20 millimeter ducts.
And how did that go?
By combining the lightweight tubeless architecture with the friction-reducing loofah sheath, they recorded a verified 12.5% reduction in overall deployment time compared to conventional high-count cables.
A 12.5% time savings on a massive multi-state infrastructure project. That translates to monumental reductions in labor costs and road closures.
Absolutely. And the durability held up perfectly as well. The entire IBR series proved fully compliant with the most stringent global mechanical and environmental standards.
Are there specific standards for this?
Yes, specifically GR20, IEC 60794-510, and ICEA S122744.
Wow, okay.
And the broader telecommunications industry recognized the breakthrough too. This technology won the 2026 Lightwave Innovation Award.
Oh, that's a big deal.
Yeah, the expert judging panel specifically highlighted it. They dubbed it a, quote, solid, well-engineered product.
Okay, but we also have to talk about the sustainability metrics, because that is a massive part of modern infrastructure deployment, and it was a key focus of this case study.
Absolutely. The miniaturization of the cable architecture yielded significant environmental dividends.
Because it's smaller.
Right. Because they removed the buffer tubes and shrank the glass, the overall cable diameter is 24 to 28% smaller than traditional high-count cables.
That's a huge reduction in volume.
It is. That reduction in sheer physical bulk led directly to a 47.5% reduction in the usage of HDPE.
High-density polyethylene plastic.
Exactly. Less plastic manufacturing and a smaller cable profile mean drastically lower shipping weights and storage requirements.
Right. Fewer trucks on the road.
Exactly.
Yeah.
When you calculate the entire manufacturing and logistics chain, it ultimately resulted in a 43 to 46% lower carbon footprint for the product itself.
So what does this all mean? Yes, reducing high-density polyethylene usage by 47% is a fantastic environmental win on paper. But honestly, the true environmental win here isn't just about the plastic inside the cable. It's the phantom emissions.
The phantom emissions. I like that.
Right. It's the massive carbon footprint saved by not sending fleets of heavy diesel excavators out to tear up 1.4 kilometers of concrete just to lay one new pipe.
Oh, yeah.
It's the hours of idling traffic jams that didn't happen because a city lane wasn't closed for 3 weeks.
The macro-level impact of maximizing our existing infrastructure is absolutely staggering. When you connect this specialized material science back to the broader digital landscape, this specific technical achievement directly shapes the future of global connectivity.
How so?
Well, think about the primary applications for this IBR technology. First, you have long-haul networks. The massive subterranean data backbones connecting major cities across vast geographical distances.
Right.
Telecommunication operators can now double their data capacity within their existing rights-of-way.
Which means they can bring significantly faster internet bandwidth to entirely new regions without triggering decade-long construction delays and endless environmental reviews.
Exactly. Next, consider data center interconnects, or DCI.
Okay.
The hyperscale AI models and cloud computing services you rely on require unprecedented continuous data traffic between server hubs.
Like constantly talking to each other.
Exactly. This intermittently bonded technology allows data centers to maximize the bandwidth inside their already congested, highly secure conduits.
Without having to drill new conduits.
Right. You also have high bandwidth 5G backhaul networks, which are required to connect thousands of new mobile towers, and enterprise or campus networks that demand rapid deployment of private, future-proof infrastructure without tearing up their own grounds.
And for you listening right now, the relevance of 200-micron glass and loofah-textured plastics is incredibly direct.
It really is.
Because service providers can use this intermittently bonded ribbon technology to handle the exponential growth of your mobile data, your complex AI queries, and your 4K streaming video. And they do it completely seamlessly.
Yep.
And they can do it without passing the multi-million-dollar costs of laying new civil works down onto your monthly internet bill.
It represents a fundamental paradigm shift in network engineering. The The perceived physical limits of legacy microducts were entirely bypassed through strategic, multidisciplinary engineering.
It's amazing.
And this raises an important, almost provocative question for us to ponder moving forward.
Let's hear it.
If we can double the capacity of an underground pipe that experts definitively thought was physically maxed out just by re-engineering the surface texture and the ribbon structure of what we put inside it, what other full legacy infrastructure systems in our cities are just waiting for a materials science breakthrough?
Oh, wow. That is a huge question.
Right. From our aging electrical grids to our century-old water lines, how much untapped efficiency is hiding right beneath our feet, just waiting for the right engineering solution to be doubled?
That is a brilliant thought to leave on. The answers to our biggest, most expensive infrastructure problems might not be digging bigger holes, but rather designing much smarter materials to go inside them. And that brings us to the end of this chapter in the HFCL Time Machine. Until next time, stay connected to what's next.
You've been listening to HFCL Time Machine. For more conversations like this, find us on LinkedIn, Instagram, and YouTube.